Okay, let's start now. Hello, everyone. My name is Tan Zhao, and I am a research scientist from Nvidia. Today, I'm really excited to be hosting this distinguished event centered around the foundation and the big models for medical image segmentation. The first talk today is continual segmentation, processing towards a unified and easily accessible segmentation model in passing 143 whole body organs in CT scans. This work was accepted for ICCV 2023. Let me introduce the speaker of the first talk, Mr. Zhanghexuan Ji. Zhanghexuan is a PhD candidate and research assistant in the Department of Computer Science and Engineering at State University of New York at Buffalo. He is an AI deep learning researcher and enthusiast with a strong passion in developing practical AI solutions for real-world vision problems. His research interest mainly spans over deep learning and its applications in computer vision, medical image analysis, and radiology. Applications include 3D CT MR organ and lesion segmentation, continual whole body multi-organ segmentation, weakly supervised tumor segmentation, interactive segmentation, multimodality segmentation, vision language representation learning, and pathological cell segmentation and phenotyping. His work have been accepted at recent MICCAI, ICCV, and other conferences. This is a joint work with Dr. Dazhou Guo, Dr. Da Kaijing at Alibaba DAMO Academy. Zhanghexuan, let's start.
Okay, thank you so much, Sam. So here today, thanks everybody here join this MICCAI industrial talk. So today we'll introduce our recent scientific work, which is a continuous learning, continuous segmentation model towards a single, unified, and non-forgetting continuous segmentation model of 143 whole body organs in CT scans. So I'll first give an introduction over our motivation. I think it's very important why we decide to use a continual segmentation for multi-organ segmentation task. And then I will give a brief introduction of the continual learning in case someone is not very familiar with this task. And then we will get deep into our models, our methods. So it contains 3 parts: the general encoder, the decoder pruning, and the output merging. And then we will show some experiments and results of our data set and segmentation performance. And then we will conclude in our contributions and future works. So first, let's introduce our motivation, right? So in real clinical practice, it is desirable to segment the whole body organs with a single model and also dynamically extend the segmentation model to add new organs. So think about the radiotherapy or chemotherapy, right? If you localize a tumor, you want to avoid all those organ risk around the tumor. So you have to segment the whole body organs, as always. Sometimes if you want to, have some more organs, target organs to segment, you always need to extend a well-trained segmentation model to add new abilities. But there's a lot of challenges for these whole body organs, right? Because first thing is a data set. So is it possible to prepare a fully labeled whole body organ data set, at one time? So this is not practical, right? Because think about how many organs we have for the whole body organs. It could be hundreds of organs, and it can always be increasing. So it's not possible to get a full annotation of a data set. So how to do this, right? We'll notice that all the multi-organ segmentation data set are actually partially labeled and sequentially built over time. So how to understand this partial label, right? So think about if you are targeting at a segmented liver, and you have a liver data set called KISS, right? So this KISS data set is a fully labeled, a fully annotation data set only for liver segmentation. But if your target organs are all the organs in abdomen body parts, right? So in this case, this KISS data set is simply a partial data set because you missed all the other abdomen organs except the liver. So think about if we have our target organs as the whole body organs, then any multi-organ segmentation data set will be a partial labeled data set, and you always miss some organs in the background. And also, in order to collect such a large data set with so many annotations, it's not possible to build the data set in one time. So you have to, simply, different hospitals have to work together and make the annotations one after another. So this data set will come sequentially. And also in medical, right, we always care about patient privacy and data storage issue. So if you are working on the multi-site data set, it's not possible to share. I mean, it's not always possible to share the data, right, between all the different hospitals. And not only the data set challenges, we also have the model challenges. So when updating model, because of the privacy issue, previous training data set may not be accessible. So there's no way to fine-tune the entire model with all the data sets previously, right? Previous data sets. And even if we have access to the previous data sets, updating or fine-tuning the entire model is still not efficient. Consider, the 3D segmentation model is super large and heavy. So the question is here, so how to train a unified model sequentially over multiple multi-site, partial labeled, multi-organ data set without access to previous training data set. So because we have this partial label issue, so we have to think about some clever way to do this. So first way is to simply do a partially supervised segmentation. So this one is actually being studied in 2020 and 2021. So this allows you to train a single model over a collection of data sets where each data set is partially labeled on the single node and simultaneously. But our data set could be the multi-site data set and sequentially built over time. So the single node and the simultaneous are not preferred in this case. So how about federated learning, right? Federated learning allows you to train a model over multi-site data set, on multiple nodes, but they still ask you to, get all the data set ready simultaneously. So this is not preferred in our case. So is there a way to, actually train a model sequentially over multiple data sets, right? The answer is continual learning. So this is actually a hot topic in recent years. And it allows you to train a single model continuously over a multi-site data set, one after another. So you don't have to wait until all the data set ready. Once you have a data set, you can incrementally add new task, new ability for the model. So before we move to the method part, I think we have to, I need to give a brief introduction to continual learning to better understand this machine learning task. So continual learning asks you to continually updating a model over a sequence of new tasks and data set with different distributions without forgetting the old knowledge of previous learning tasks. So this is a definition of continual learning, right? If you have a sequence of data set, for example, you have D1 all the way to DT, so at a different task, different step, you only have access to the current data set called DT. And you have a subset of organs or classes compared to the entire union of the classes, right? So after the entire continual learning training, so at the last, you will have the model which can segment all the target class. And you notice that in order to add new models in new classes, right? The model could experience the forgetting because the deep learning model, when you fine tune the model, the parameter will change, right? So the parameter change is called plasticity, right? It causes the model to forget the previous learned tasks. And the application of incremental learning in semantic segmentation is specifically called Continual Semantic Segmentation, or CSS. So for example, right, at different steps, you have different targets. For example, step T minus 1, you have person as your target, and step T, you have car, and then you have bike, right? But notice that, in this case, your background is not actually the real background. You could have some past learning objects or the future objects, right? So this phenomenon is called background shift. So after we see the computer learning, right? So now I think we can define the problem. So motivated by the aforementioned challenges, we formulated the whole body organ segmentation as continuous semantic segmentation problem. So continuous learning, we continuously train identified model over multi-site, partial labeled, or multi-organ dataset, sequentially built over time to segment whole body organs without catastrophic forgetting and the excess to a previous training dataset. So just like this one, right? This is the illustration of the CSS. So for example, we have a head and neck organ dataset at hospital 1. Then we start our model training at hospital 1. And after that, we move our model to hospital 2. So at this point, we lose the access to the previous dataset. And now we have a new dataset which targets at maybe chest organs. Then we updating the model on this new dataset, and then we move the model to the hospital 3. So in this case, for example, we have abdomen organs. So we lose access to the previous tasks, but we can update our model to the new target organs. So here is several requirements for a medical continuous segmentation method, right? We still want the accuracy, we do not want forgetting, and we have to care about the privacy, so we don't have the access to the previous training dataset. And we want to efficiently update the model. So how to do this, right? When we design our method, we want to select some, continuous learning methods from the 3 different categories. So first is rehearsal-based methods. This, guarantee a high performance, but it requires you to store and replay exemplars from all dataset. So obviously, this is, not fulfill the privacy issue. And for the regularization-based method, it can allows you to, do the knowledge distillation from the old model to the new model, and do not requires you to save any exemplars. However, because you don't have the the access to the old dataset, and you still want to use knowledge distillation to fine-tune the model, so there's actually no performance guarantee on old tasks. So what we decided to use is architecture-based method. So this one, in this case, we can freeze the backbone and extend new layers or new branches for each new task. In this case, the backbone is frozen, and the decoders, the branches are independent with each other. So there's literally no forgetting, and we do not require the memory. So I propose to use the architecture-based method, right? And now, so how to prevent forgetting and guarantee performance? Well, the answer is to train a representative general encoder on the initial task, and then freeze it afterward. And also, we need to add separate decoders for future tasks, independently. And how to, because if we want to extend the new branches for each new task, there will have an issue about model parameter linear increases. So we have to think a way to limit the parameter increasing. And in this case, our answer is no, we simply prune each decoder at each learning step to restrict the parameter increasing. And after that, because the model train different tasks with different decoders, so it's more like a multitask model. But we still want a single segmentation result, right? So I have to merge the predictions for all the decoders. So there's a lot of way to do this. You can simply use the ensemble. You can in this case, we're using a confidence-based output merging. So we'll introduce each part now. So this is our framework. So it contains 3 parts: general encoder, optimized and pruned decoders, and anomaly-aware output merging. So this part is general encoder, right? So we start with the training, the general encoder on the first task with 2 auxiliary tasks. And then each time we add a new data set, we train a new decoder. And then we do the optimization and pruning to decrease the decoder parameters. And during the inference, we have to merge all the predictions from all the decoders using our anomaly-aware output merging. So specifically for general encoder, we train a general encoder, which is a NUNet-based backbone on a relatively comprehensive dataset as initial task, which covers more target organs and body parts in order to train the general encoder to have a better representation ability. So we recommend starting with a public dataset called Total Segmentator, so which covers whole body, which has over 100 organs and over 1,200 patients. So this is totally enough for the general encoder training. And besides the segmentation task, right, we also have two auxiliary training tasks. One is body part segmentation. So we want the model to segment the different body parts, right, out. So during the training, the model can know like which the 3D scans belongs to which body parts. And the body part label is this is clever. This is from XUCT scores predicted by previous work, which is a automated body part regression algorithm. And we also include a tumor segmentation here, right? So tumor segmentation, we train the model has the ability to recognize and segment the dedicated tumors from a tumor data set. And for the decoder optimization, we have to first do the optimization, right, using a neural architecture search or NAS. So we want to replace, in this case, the 3D convolution kernel with projection kernel, 2D kernel, or pseudo 3D kernel. When doing the search, if these kernels provide better result, we will replace the 3D kernels. And also, this not only optimizes the decoder performance, but also reduce the parameters. So as you can see, right, so consider the 3D kernel has 100% parameters, then the pseudo 3D only has less than 50% parameters, and 2D is 1/3. If you can replace it with a projection layer, it will be super light. So the NAS not only optimize the performance but also reduce the parameters. And then we will use a teacher-student based knowledge distillation to prune the decoder in order to further reduce the parameters. So we treat each, from bottom to top, we treat each convolution block as a teacher, and we want to use the distillation method, to replace the decoder, the convolution block with a projection layer. So if the replacing will cause a dice drop less than a given threshold, so in this paper we used 100%. So if if replacing the block with a projection layer and the dice drop is less than 1%, then we accept this replace. And so in this case we replace a heavy convolution block with a super light projection layer. And this process goes from bottom all the way to top. And after this process, the decoder will be compressed by a super high rate. The third part is anomaly aware output merging. So because we always need a way to merge everything together, right? So think about the effective. We noticed that for example, if we train a decoder on head and neck organs, so this decoder actually only seeing the head and neck region without any knowledge of abdomen and hip and thigh, right? So when you have a whole body of scans and send it to the model, it will pass the head and neck decoder. And this decoder, since it never see the abdomen region, so it will have some false positive segmentation in these regions. So we want to remove this part from before we do the merging, right? So what we do is use an entropy-based confidence weighting method. So for each new data set and task, we first pre-compute the average body part distribution map over all body parts. And then we store the task-specific body part distribution with the corresponding decoder head. So when during the inference, we combine the predictions from all decoders using this confidence weighting method. And the weighting map is calculated using the previously computed, the body part distribution map of each decoder, as well as the tumor prediction map. So in this way, each decoder will know like which part is, it has more confidence with, and which part, if the 3D scan is contains unseen body parts for that decoder, it will simply gives us very low weights, very low confidence, as well as in the tumor regions. So for the experiments, right, we used 4 different multi-organ datasets, which in total we have over 2,500 patients and 143 organs. So the details of the dataset is given in this table. The total segmentator is a public dataset, and all the other datasets are private dataset. So as you can see, right, the total segmentator has over 100 organs, but in most cases it's bones and muscles. So in our chest organs, we include some major organs, muscles, and a lot of vessels within the chest regions. And we also include a head neck organ, which contains 13 head neck organ at risk. And the last one is a esophagus organ, which contains only esophagus segmentation, but with advanced cancer. We also has, in order to validate the robustness of our framework, we designed 2 different CSS orders. So the order A will start with total segmentator, and then goes to the chest organ, then head neck organ, and the esophagus organ. For order B, we exchanged the chest organ and the head neck organ. So here is a comparison to the leading CSS methods. So this table gives the final result, after all the continual segmentation training. The final result of 2 orders on different datasets, as well as the overall dataset, overall organs. So as you can see, right, for example, in order A, our method has, about 93% on total segmentator, while the other method, second best is only 42%. And on chest organ, we are still, very far exceeding the other leading methods. Also on the head neck organ. So because why other methods has such a large drop in the performance? Because of the forgetting. So those methods, most cases, they are regularization based. So they will, when they fine tune the model, there will be a large forgetting over a different data set. And the overall performance on all the organs will have around like 88%, right? So the second best is only 42%. And for order B, it's the same thing. We still have a very high performance. So one thing to notice is, no matter for order A and order B, our result is exactly the same, right? Our final result, because our method is order invariant. Think about it, right? It's because our encoder is completely frozen, and each decoder is independent with each other. So no matter what orders you come, it always gives you the same result. But for all the other methods, they are, sensitive to the continual learning, steps, the orders. And also we provide the upper bound over each individual dataset. So as you can see, right, the upper bound of total segmentator is 93%, where we are reached 92%, almost 93%. So it's very close to the upper bound. And the same thing happens to all the other organ sets. So that would say that our performance is very accurate and close to reaching the upper bound. And also, we need to focus on the parameter size, right? So all the other models are using the original NUNet model, which is around 15 megabytes. And although our model, we keep increasing the decoders, right? But because of the pruning, our whole parameter size is only, it's slightly less than 15 megabytes. It's only 98% compared to the original NUNet. Oops. So this one is the forgetting curve of order A and order B at each continual learning step. So as you can see, right, we start from the total segmentator, and after each step, all the others method are keep forgetting the previous tasks, the previous organs. well, our methods almost keep the stable performance. You still keep the accuracy. So this shows that our method is it has no forgetting and the stable performance. And there are several ablation studies show the effectiveness of different parts. So this one is a table gives a one-step CSS scenario from total segmentator to chest organ and head neck organ. So we test whether freezing or not freeze the general encoder. So as you can see, right, when freezing, we have a very stable performance. But when unfreezing, the dice score on total segmentator drops a lot because of the forgetting. So that's why we have to do the freezing to keep the model unforgetting. And this table shows the effectiveness of the parameter, the decoder optimization pruning. So focus on this first column with 100% as the threshold. So within a 1% threshold dice score drop, total segmentator after pruning only has 43% of the original decoder size. And for chest organ is 23%, head and neck organ is 28%. And for this very simple, S organ, which has only one target organ, we, after pruning, we only have like 4% of the original size. So this is so our pruning method is very effective for model compression. And this table 4, we compared a simple ensemble with our anomaly-aware output merging method. So as you can see, right, our method has much higher and stable performance than the ensemble because we can, simply recognize the unseen body parts and remove the false positives. And here we have a quantitative result about different body parts. Compared our methods with MIB and PLOP, which are two leading methods for CSS models. So as you can see, right, the yellow arrows gives you the false positives or false negatives, the missing predictions of the MIB and PLOP. As you can see, there's a lot of organs which has false negatives, the missing parts, or the wrong predictions. But in our case, right, we keep a very stable and accurate segmentation, no matter in any body parts, in any organ groups. So this result shows our method is, our model is accurate, stable, and also no forgetting. So now we can reach to a conclusion about our contributions. So we're the first to comprehensively study the multi-organ CSS problem to more sufficiently and efficiently support medical, to support medical diagnosis and treatment planning purpose. So our clinical desire number, we include a clinical desire number of organs, which is 143. There's a lot of organs included. And also our model, we cross different body parts, right? The head, neck, chest, abdomen, and the pelvis, hip and limbs. And we propose the first pure architecture-based multi-organ continuous segmentation framework. So in this framework, we avoid catastrophic forgetting in CSS, and we're the first to integrate and unified encoder in CSS. Well, in traditional continual class incremental learning, the unified encoder has just been applied in last year, and then no work has applied the unified encoder in segmentation, continuous segmentation previously. And also, we're the first to apply a model pruning in CSS to keep the model scalable and maintain a limited model complexity. And our model continually trained and validated on 3D CT scans of 4 different datasets over 2,500 patients. And we segment total of 143 whole body organs with a very high accuracy and close reaching the upper bound performance level of 4 well-trained individual models. So our conclusion about this work is our new multi-organ CSS framework avoids catastrophic forgetting while effectively segmenting new organs with high accuracy, closely reaching upper bound performance level of 4 individual models. And each part of our the general encoder, the decoder pruning, and the anomaly aware output merging demonstrates their effectiveness and support the model to avoid the forgetting, restrain, limit the decoder size, and also shows the promising performance over different body parts predictions. And for the medical society, we actually provide a general and practical solution for whole body organ segmentation. And I believe this one has a great potential to sufficiently and efficiently support medical diagnosis and treatment planning in the future. All right, so this is all about our work. Thanks for listening.
Thank you, Zhanghexuan. It's truly a wonderful talk. I saw there are already questions in the Q&A box, so let's answer them first. Yeah, let's answer them first. If you have new questions, could you help wait till all these 3 talks are finished? We have very limited time. We need to make sure that all the talks are covered. So let's start from the question from Wenjia. A question perhaps for the okay, that's for the presenter later. Anyway, let's go to the second question. So if the different CT data sets have different dimensions or spacing, can we still train the model?
Yes, because any unit will simply, resample, pre-process all the data sets, all the images to the same spacing. So even if the different data set has different dimensions or spacing, it's totally fine for the any unit, the backbone to accept to pre-process those images into a same predefined spacing. And also the NUNet is using using a sliding window to crop the 3D, whole 3D scans into different 3D patches and send it into the models, and then they actually stitch all the patches together back to the entire prediction map. So the answer is yes, it can handle different dimensions and spacing.
Yeah, the second question is the implementation available online, like on GitHub? This will help other researchers to use in the ongoing work.
Yeah, that's a good question. Currently, we're still have some following work on this project. So because it's it's a medical data set, it's a company project. So at this point, we're still preparing for the online encoding and also the models. But I believe by the end of the year, or maybe the early in next year, the model will be accessible online. We will. I think we are planning to put this model on the cloud, so anyone can try the models. Yeah.
Thank you. A question from Fausto. Maybe I didn't catch this detail during the discussion so far, but how did you obtain your frozen encoder? Was it trained through the self-supervised learning or something like that, or trained specifically for some task?
Oh, so yeah, so in this work, right, we're not using the self-supervised learning. So we start, as I said, we start with a comprehensive data set. We start with total segmentator. So it's a labeled data set with over 100 organs and 1,200 patients. So it's large enough, and it contains a lot of organs to train, to simply use the segmentation task to train a general frozen encoder and make sure that the encoder has a good representation ability. And also it contains a tumor segmentation task as an auxiliary to increase the encoder performance, as well as the body part segmentation. So all these different tasks, as well as the comprehensive total segmentator dataset, promise the frozen encoder to have a good representation ability for downstream tasks.
Thank you. A question from Shaorong. Did you try multiple data for the same anatomy? will the continuous learning order matter?
Yeah, so multiple data from the same anatomy. If you're talking about like continually train different organs within the same body parts, for example, everything we keep increasing the organs in the chest organs, right, in the chest region, then actually, you instead of using continual learning, you can simply use pseudo labeling, because each step you always see the same anatomy, same body parts. You just trying to add new organs which are previously background, right? Background. So in this case, but in our model, right, our continual learning order are always invariant, because we every decoder for different tasks are independent with each other. So the order doesn't matter in this case.
Thank you. A question from Anna. Do you train by patches for 3D CT segmentation?
Yeah. Any unit is a patch-based 3D segmentation. Yes. Yeah, and the resolution, the resolution for CT scans are predefined as 0.75 by 0.75 millimeters by 3 millimeters in axial direction. And a tumor lesion, tumor lesion catch a very small volume. Yeah, you're right. So in our case, we're majorly, trying to segment all the organs here instead of the tumor. Tumor segmentation is simply, just auxiliary task in order to improve the general encoder, as well as used in the final output merging part.
Yeah, thank you. A question from Tom: how is the continual learning when you freeze the layers? Essentially, you don't forget, but because the layers are frozen, but you also don't learn anything anymore. As it's not correct to call this continual learning without forgetting. It's just freezing. Also, you mentioned you motivated the study with creating one model. However, the proposed method basically trained individual models for each new task that have absolutely no frozen layers in common. So they are essentially completely independent models instead of one joint model.
I would say, this is the first. So the second part of the question, right? So it's more likely a multitask model. So different decoders handling different tasks, and we use the output merging module to make sure that we collect a single predictions over all learned organs. So yeah, that's right. Because why we have to freeze the model, as I said in our motivation, because currently for a medical data set, we care more about the accuracy. So we have to make sure that without forgetting, and as I said, any kind of disturbance or fine tuning of the backbone or the entire model will cause the parameter change, and it may lead to some kind of forgetting. And as our results showing, right, the forgetting of the previously those leading datasets methods are super large. So if we're using any kind of fine tuning of the entire model, at this point it's very hard to reach a high accuracy non-forgetting model. It's simply because this is it's still a practical method. We want to support the actual hospital diagnosis and other purpose. So we care about the performance more than simply just use some methods to fine tune the entire model. But also because why we call this continual learning, because if you check the CVPR paper 2 years ago or last year, so there's two works. One is from Google and one is from Amazon. So the Amazon paper, they actually they also trained the backbone over 800 classes and then freeze the backbone and keep adding the branches. And that paper actually has a very high accuracy. And in that case, we call that model continuing incremental learning model. So I think, for continual learning, it's not necessary to, you can always freeze some part of the model and increase some part of, the model to handle a new task. This is called architecture-based methods. This is one of the three, continual learning methodologies. So I would say, this, even if we freeze the models, is still a continual learning framework. Right.
Thank you. Thank you. And for the first question from Wenjia, sorry, I misunderstood your wording. So Wenjia has a question: when a new task head is added and trained for a new dataset, which has overlapped organ types with previous datasets, how does the network avoid forgetting the learned information on the previous datasets?
Where is Wenjia's question here?
It's the very first one.
Oh. Yeah, if there is the overlap organs with previous data set, right? So, in this case, it's more like, so if like two models are predicting the same organs, so it's more like an ensemble. It's basically based on the so-called, the confidence map, right? So we trust, for example, if the two decoders predicting the esophagus in the same time, it's simply, just ensemble the result together. And the result, the dice score, it looks like there's no forgetting, right? Because, but actually, there's a very slightly change in the dice score. But, because we're trying to segment the organs instead of the tumor. So normally speaking, the organs, you always have the similar segmentation, and the only difference in the segmentation mask is on the boundaries. So because we're reporting the average dice score over the 100 organs, right? So even if there's a slightly different predictions in the dice score, you cannot see that in the percent, in dice score percent. But yes, your question is correct. There will have some changes if there the organs are overlapped. But because it's ensemble, so I would not say it's some kind of forgetting. I would say it's it's more like an enhancing in this case. Yeah.
Thank you. Thank you, Zhanghexuan. So because of our time is limited, we don't have time to answer all the questions live. So if possible, could you help answer them from the QA chat box? That would be very helpful.
Sure. Yeah.
Thank you so much. Thank you. Let's go back to the second talk. And if you have more questions, welcome to type in the Q&A chat box. Just include which talk you are asking about, like talk 1, talk 2, or talk 3. Thank you. So let's go to the second talk. The second talk today is Anatomical Embedding Learning from 3D Medical Images. This work was also accepted for ICCV 2023. The speaker of the second talk is Mr. Heng Guo. Heng is a senior algorithm engineer at Alibaba DAMO Academy. His research interests lie in the interdiscipline of deep learning, medical image analysis, and their clinical applications. During the COVID-19 pandemic, the team he is in has been awarded the Advanced Collaborative Achievement in Technological Anti-Epidemic Efforts. He holds a BS and MS degree from Shanghai Jiao Tong University. Welcome.
Thank you, Dr. Zhao, for your generous introduction. It's my privilege to have this opportunity to talk to you about our recent works in this great webinar. My theme today is called Anatomical Embedding Learning from 3D Medical Images. My name is Heng Guo, and I am a senior algorithm engineer from Alibaba DAMO Academy. I'm going to start this talk through three basic questions. The first one is, what is the anatomical embedding learning? A possibly not so exact description might be the process of extracting meaningful representations or embeddings from 3D medical images that capture the anatomical structures and feature presentations present in the images. This description may not be so straightforward, and naturally, there will be a second question: what is the advantage of this thing, and why do we need it? I think its use cases include, but are not limited to, fast matching and registration. As illustrated in the top right figure, we can select a point in the template volume and quickly find the corresponding point with similar semantics in another query volume using methods like nearest neighbor search. The second application is to provide better initialization for networks, which will be discussed in detail in the next half of my talk. Another application is steerable pathing of allotomies, as shown in this figure. We can directly retrieve the anatomic structures of interest from the image. For example, fifth right rib, first lumbar vertebra, or simultaneously parsing pancreas and spleen. The technique to achieve this will also be covered in today's talk. The final question is how to get this anatomic embedding. I will talk about our recent explorations on roughly two paths, self-supervised and supervised. So here is the outline of my talk today. It mainly has two parts. One is an author paper from ICCV this year, and we are very appreciate for that recognition. A lot of credit goes to the first two authors, Yankai Zhang and Minze Sun. They were exceptional interns with us before. The second work is a project that I led, and of course, it is also a collaborative effort with my colleagues. It is currently in the process of being submitted for publication. Now let's begin the introduction to the first work. We all know that data annotation in the medical image field is very time-consuming and labor-intensive, and they usually rely on radiologists' expertise. So naturally, people have started exploring how to utilize self-supervised learning methods for pre-training on a huge amount of data, and then fine-tuning on a small amount of label data to improve the model performance. If this training paradigm is effective, we can regard it as the model learning better anatomic embeddings during the pre-training process, so providing improved network initialization for the fine-tuning stage. We gave this work a beautiful name, Alice, which observant viewers might have noticed is hidden in our title. During our literature review, we found that recent mainstream self-supervised methods can be mainly categorized into three parts: contrastive learning, mask image modeling, and the combination of both. Next, I will briefly review these works. When we talk about contrastive learning, we cannot bypass these pioneer works. From the perspective of network architectures used, they can be roughly categorized into those based on CNNs and those based on transformers, although there can be other categorization methods as well. Due to time constraints, I cannot go through one by one, but I would like to mention four notable works: SimClear, MICCAI, DAMO, and Bio. The core idea of SimClear is to improve model performance by augmenting data with multiple views of the same sample and learning feature representations through contrastive loss. Earlier version of SimClear might suffer from model collapse, but MICCAI introduced a momentum teacher strategy to alleviate this issue. And then DAMO also adopted this momentum approach and used a student network to predict the outputs of a teacher network, while employing feature sintering and sharpening to prevent model collapse as well. Moreover, Bio proposed an asymmetric network structure and demonstrated SOTA results without using any negative samples. Then we come to mask image modeling part. in the past year, there has been a surge of research in this area, partially driven by the work named MAE, masked autoencoder, proposed by Kai-Ming He. In fact, much earlier, there were works using image reconstruction for visual pre-training, although they were known by different names at that time. Today's new methods can be simply classified into two categories, reconstructing the original image or reconstructing the image features. The final category of related works combines contrastive learning with mask image modeling. The motivation behind these approaches is to leverage both discriminative and generative tasks to achieve stronger embedding learning. Compared to previous methods, these approaches appear to be more complicated. For example, I bought samples 2 instances from a given input, then applies masked data augmentation and the regular image augmentation to each instance, so resulting in 4 inputs. These inputs are then fed through the network, and the model receives cross-class token supervision and in-patch reconstruction supervision. Notable works in this category also include DARA and SSL string UnityR published in CVPR last year within the domain of medical image analysis. Okay, let's consider the challenge in contrastive learning. The most difficult challenge is that the views extracted from the same image can be unrelated. Please look at this figure. The content gap is huge. A method named contrastive crop get most relevant crops like this. Using the training, using the locates object training using the information in heat maps, so they get effective samples like this. So another technique named logo maximizes the similarity between global crops and while allowing the local crops to remain distant from each other. They also solve the similar problem. However, in medical imaging, we ask ourselves how to locate body parts with semantic labels and how to leverage the intrinsic similar anatomic structures across varying medical images volumes. Existing strategies usually treat crops from the same volume while containing non-relevant contents as positive pairs. Our answer is to using SAM, which is not the segment anything model that attracted a lot of attention this year. It's proposed by my colleague, Dr. Yan, in TMI 2022, titled Self-Supervised Learning of Pixel-Wise Anatomic Embeddings in Radiological Images. The model is also called SAM, which can support fast key point matching and supporting, as we mentioned at the beginning of this talk. The answer to the second question is redefining the positive and negative samples, which means we use crops that contain similar semantics, but from different volumes as our positive samples in our pipeline. Let's also consider the challenge in mask image modeling. The existing methods mainly focus on 2 problems, constructing more sophisticated masking strategy and constructing various reconstruction objectives. However, when we consider the combination of contrastive learning and mask image modeling, we find that existing methods can be somewhat simplistic in handling masked views and augmented views, especially when the masking ratio is very high. Directly pulling 2 seemingly unrelated features in such scenario may not be reasonable. Our solution is to perform feature alignment and proposed a conditional anatomic semantic alignment module. We named it CASA. This is part of our pipeline. As we can see, the CASA module handles the features from online decoder DS and the target encoder ET, and the attention and the target encoder ET. So the attention mechanism using a query computed from the online encoder ES, where the features are only from visible tokens computed or visible tokens of masked views. The insight behind this design is that we use the common parts between masked views and the full views to construct queries. And these queries can be regarded as connections between masked embeddings and original embeddings. This is our full pre-training pipeline. We first use a pre-trained set to get anatomically similar crops from various volumes. Then we perform masked augmentations and the regular augmentations separately. So we get two masked views and the two augmented views. Then these views go through the networks to perform masked image modeling and aligned contrastive learning. Next, we break down this diagram into details. These details are fully elaborated in our paper, and here I only talk about some high-level objectives in our pipeline. For intervolume modeling, that is mining diversified views from different volumes to learn anatomic features that are universal across similar body parts. In this figure, for example, we use class KV that is from a global average pooled feature from the full view to supervised class QU that is also a global average pooled feature, but from the masked view to fulfill this. For the aforementioned CASA module, we aim to optimize the intra-volume relationship by maximizing the similarity between views from the same volume. The computation graph is the regular attention mechanism, but something to be noted is that we generate consistent contrastive pair from output features of the online decoder and the target encoder, while the online encoder serves as the guidance. It might get some time. Additionally, the notations in this work can be a bit confusing at first glance. It might get some time to fully grasp them and avoid any confusion. Then we come to the experiments parts. We use 2,000 unlabeled cities from FLAIR 2022 MICCAI challenge as a pre-training dataset. The downstream tasks include FLAIR 2022 and BTCV multi-abdominal organ segmentation, and the most-made dataset for COVID-19 classification. We use DICE and NSD as the segmentation matrix, and AUC as the classification matrix. We apply our pre-trained encoder weights to various VIT-based segmentation networks designed for medical tasks of Unity Informer and SUNY by following their settings. And we have compared these backbones on the different self-supervised pre-training frameworks. Alice outperforms them by at least absolute 3.74% in DICE. We also compare Alice with strong CNN-based self-supervised methods and baselines. Three conclusions can be drawn from these results. First, transformer baselines tend to achieve better performance than CNN counterparts after properly pre-training on FLAIR dataset. And second, masked image modeling-based methods tend to perform better than contrastive learning methods. And finally, combining masked image modeling and contrastive learning can further boost the performance. We also compare Alice with other SOTA SSL methods on the BTCV offline and online test set. As shown in this table, Alice, without using any ensemble strategy, still achieves the competitive performance with the best DICE on both offline and online test set in COVID-19 classification setting compared against strong VIT-based methods. Alice significantly outperforms them at least absolute 3.15% in AUC. It proves that the effectiveness of modeling anatomic invariance and performing semantic alignment to assist the self-supervised learning process. We investigate the effect of leveraging the intrinsic anatomic structures of different volumes to model the anatomic invariance or anatomic embedding. We feed the same body part of different of query volume and the key volume to add another SSL method, IBOT. The performance gain on DICE is 1.37% and 1.24% on NSD respectively. We also investigated the effectiveness of the custom module. Our approach can be applied to most general CMS architecture-based SSL methods. All methods achieve more than 1.21% absolute dice gain on the FAIR 2022 dataset by adopting CASA. Finally, we observed that using cosinus in ALICE achieves slightly higher performance than info-NCE loss on FLAIR data test set. Thus, we do not utilize negative samples and use cosinus as the default for the contrastive learning branch in ALICE. Here I demonstrate some qualitative visualizations. We can see that ALICE produces sharper boundaries and generates results that are more consistent with the ground truth in comparison with all other models. Well, here we come to the second part of my talk. Actually, earlier than the ALICE work, we were considering how to directly locate the allotomies of interest based on our research focus. For example, in this radiology clinical paper, researchers care about the lumbar L1 trabecular attenuation values. Can we directly point out the location of L1 instead of segmenting out the whole spine, then split the L1 out? So this motivates us to develop a more steerable framework to achieve this. We hope this framework can be steerable as well as robust and efficient. So finally, MICCAI is realized. We start from the RIB instance segmentation task because this kind of anatomical structures are sufficiently difficult. They are elongated and oblique in our chest. If our framework can achieve a steerable passing on this kind of structures, it can generalize well to other structures. We first curate a dataset called RibInst. It consists of 420 cases in training, 74 cases in validation, and 160 cases in testing. We adopted a cascaded pipeline to perform this task. The core is the steerable allotomy detection stage in the bottom. It is based on the advancement of transformer-based detector. We extended it to a full 3D space setting so that we can estimate position, scale, and rotation in a single forward pass. And we propose a steerable banding technique to map query embeddings and ground truth labels. These query embeddings are the highly compact anatomical embeddings that can help us locate expected allotomies given input image. In this work, we also investigate some popular anchor-free detectors in our LIDOF setting, that is Centrate and FCLS. We carefully implement some adaptations but reserve the original spirits of these two frameworks. As can be seen in the detection result, MICCAI achieves the best identification rate of 97% with a moderate amount of parameters. Notably, compared with pure CNN architectures, MICCAI can infer at least 10 times faster in terms of latency. In this detection visualization, we show normal results in superior to inferior view and a limited FOV case in posterior to anterior view, and a case with rib adhesions. And finally, all the odd number labels are queried, that is rib 1, rib 3, and rib 5, etc. Ground truth labels are rendering as value reference. In segmentation results, we also compare to a strong baseline method called UNET. MICCAI achieves the best dice of 19.9%. Notably, the whole pipeline of MICCAI can be finished in less than 3 seconds. The efficiency is attributed to our detection then segmentation paradigm, which detects on low resolution with global FOV and segments on high resolution with local FOV. An example with the broken structures is visualized at the bottom right. Following the same principle, we have performed vertebral and multi-organ segmentation. Like before, they also go through the ROI extraction, allotomy detection, and finally segmentation and merge. Since our framework is decoupled, there can be some customized design of whether to merge some organs based on some prior knowledge. Based on MICCAI, we introduced one downstream task called opportunistic osteoporosis screening. This work has been accepted by RSNA 2023 as the post presentation. In this work, we tackle the bone mineral density estimation problem using paired CT DEXA data. DEXA is short for dual energy X-ray absorptiometry, which is the gold standard of BMD examination in the routine clinical use. However, for the lumbar spine, it can only report the results of lumbar L1 to L4. With the spine passing by MICCAI, we can recognize which vertebrae have ground truth and which are not. Then a self-supervised solution is proposed to perform accurate BMD estimation, and we have achieved AUC of 0.96 in a single center. Finally, I will briefly summarize today's talk. We first introduced ALICE, a self-supervised pre-training framework. In this work, we mine positive pairs across volumes and we perform anatomical feature alignment. And secondly, we introduced MICCAI, a steerable, robust, and efficient medical image segmentation framework. We taken 3 anatomy parting tasks as examples: ribs, vertebral, and abdominal or multi-organ segmentation. Then we introduced osteoporosis screening as a downstream task. Some useful resources can be found in the listed links. Finally, thank you everyone for listening and watching. I would like to end up with an advertisement that we are hiring both for research interns and full-time positions. If you are interested or if you have any question, please drop me an email. Thank you.
Wow, that's a very useful advertisement. Thank you, Heng, for the wonderful talk. So there are a few questions in the Q&A box. A question from Avyata. Very interesting work. Can you provide a link to paper about your research or GitHub page? So is it open source?
Yes, it has been open source. 2 of my works have both open source in the list links.
Oh, great, thank you. A question from Che. May I ask the implementation on the CT classification task? Since the model is pre-trained on patch-based input, so it extracts the local embedding for this patch. But in classification, we require the global embedding from the whole CT to classify the label. Is there any special strategy in classification or only train with patch and inference with whole CT?
Okay, the specific classification task training strategy can be found in your supplementary material. So there are more details, so you can find useful in that material. Thank you.
Thank you, Heng. So let's go to the third talk. Third talk is advancing whole brain segmentation with 3D medical visual foundation models. The speaker for the third talk is Dr. Yucheng Tang. Yucheng is a research scientist at Nvidia and Vanderbilt University. He completed his PhD at Vanderbilt University and BS at Tianjin University. He was a member of Vanderbilt Institute of Surgery Engineering and a teaching affiliate at the Computer Science Department. His research focuses on innovative clinical use for medical image analysis techniques and developing data-centered artificial intelligence for clinical decision-making. He has published over 50 peer-reviewed articles including top conference papers of CVPR, ICCV, NeurIPS, WACV, MICCAI, and journal publications of Nature, TMI, Media, and Radiology. So let's welcome Yucheng.
Hey, hello. You can hear me, right?
Yes.
Okay. Thank you for the general introduction. Very appreciative. Looks like we are having very limited time. I will try to shorten my talk, and we can at the end of my talk, I will show some integrations of our current whole brain segmentation software. Okay, so let's get into our talk here. So this work is a very good teamwork and collaborated with or across the Nvidia Corporation and Vanderbilt University. And we have our radiologists from Vanderbilt University Medical Center and our collaborators from Google Cloud AI and Siemens Healthineers. And this work is a very great work done by our first author, our PhD candidate Xin Yu from Vanderbilt University. So, yep. So let's talk about our foundation model about in medical domain. So the medical foundation model is a remarkable feat of technology and innovation, and which are capable of processing the vast amount of data at large scale. And the foundation model has been trained on diverse sources of information, including the images or the other modalities such as the clinical records like genomics data or time series signals of healthcare. So the robust foundation models that can span the entire spectrum of medical knowledge. That's the goal for the foundation model. And also, as our two former speakers mentioned, that the foundation model can also have the capability of tackling the very challenging tasks of the large amount of anatomies in medical image segmentation. Like, for example, the whole body segmentations with over 100 anatomies across human body. And this is the same situations in the human brain. So in my section, I will focus on the whole brain segmentation, which is essential in the scientific and clinical investigation for understanding the human brains, which can provide us a non-invasive tool for quantifying brain structures from MRI images. And the accurate whole brain segmentation can enable us to model normal anatomies with some precisions. And by segmenting the brain into its structural sub-areas, the model can provide an intrinsic map of the human brain's structures. And a comprehensive understanding of the human brain's composition is very invaluable for researchers and clinicians, such as the neurological diseases or investigating psychiatric diseases or some neurosurgical planning. And one of the primary challenges lies in the sheer scale of this problem is that with more than 130 classes to identify or delineate the whole human entire brain, the model must contain with a colossal amount of data and information. So this complexity makes it an incredible challenge for traditional or deep learning or machine learning models to learn or accurately represent the intrinsic and interconnected structures within the brains. And this brain architecture, such as the fine boundaries between the different regions and substructures, pose another significant challenge. Like deep learning models or machine learning models often struggle to capture these subtle details accurately. So as a result, the segmentation errors can occur, leading to a misinterpretation of critical brain regions. And to deal with the local anatomical variations from the imperfect registration of human brain, we have our prior approaches utilize some patch-based networks ensemble methods, such as the prior state-of-the-art methods called SLANT, which is named as a spatial localized atlas network, tightly trained on 27 units to ensemble a whole brain segmentation in a single volume. This is a tremendous challenges for the current machine learning model because ensembling a large amount of sub networks or train 27 3D units and then ensemble that costs of a lot of time and computation resources. So take a closer look at how many brain anatomies here we are targeting the problem are. So you can see there are 171 tissues from the navigation of the intrinsic landscape of the human brain. So you can see the anatomy from ventricle structures to the gyrus tissues presents a monumental challenge for the accurate segmentation and understanding. And here's a draft view of each anatomy, the brain volume, showing the accurately segmenting these interconnected structures are very, very challenging. And so this is our research goal. So research goal is dedicated to develop a efficient and low-cost whole brain segmentation methods or approaches for the 3D MRI T1 video images. And with the goal of achieving the leading performance using a single model of all 131 brain anatomies, we aim to capture the local variations in heterogeneous brain tissues. And we try to understand the impact of data efficiency and the pre-training data size, and then ensure model scalability. To promote the transparency and collaboration, we also open source our codes and train the models. And we also have our software integration development. And we have the innovation advancements in the field of brain analysis and for improved healthcare outcomes. Okay, let's go to more details about our datasets. Our study utilized the training cohorts comprising 45 T1 weighted MRI scans sourced from the OASIS dataset. And also we have the 131 distinct labels hand traced by our radiologists. And also we augment our datasets with a diverse range of multi-site T1 weighted MRI scans gathered from various research projects. You can see the table here. We have around 5,000 T1 weighted brain volumes used as large-scale accelerate training datasets to further enhance the robustness of our model. We will cover later about how we utilize these images and how we generate the pre-training data and how we utilize the hand traced 131 manually annotated data for fine-tuning. Okay, so the pre-processing step and registration step comprised of a standard registration process to map the patient's brain volume into an MNI space. MNI space is a pretty standard registration reference space for neural imaging. And before input into the neural networks for segmentation, which we call our model the UNEST. So we do the registration, and after we got a segmentation from the MNI space, we transform back to the original image space. This process allows us to obtain the final predictions that are spatially aligned with the initial data, ensuring the clinical relevance and applicable of the segmentation results. And here's the overview of our proposed model architecture with the hierarchical transformer encoder and a CEN-based decoder part, which can achieve the better local spatial representation learning, improve efficiency, and reduce the model complexity. So here for a more detailed look here, so we have the input image volume are embedded into the patches and then in each hierarchy. So we split the patch embeddings on downsample the blockified before being fed into the transformer encoder, and then we have the outputs are deblockified back to the volume plane. So this is the how the hierarchical transformer are formulated, and we use this hierarchical transformer encoder as our main image representation learning encoder here. And then we have a skip connections and bridge into the decoder part, which is our CEN based. I will skip the very detailed part of the how the networks are designed. We can think offline if anyone is interested in the theory part of the architecture. And we also for the encoder part, we also employ the spatial nesting operations in the 3D blocks to form a local attention hierarchical design. So this design enables us to reduce amount of model complexity, which is different from the swing transformers, which utilize the global attention among the shifted windows. In our design, so transformer encoders are applied to each volume block separately to achieve local attention, which each block being modeled independently. And information across blocks is communicated by the aggregation modules. And this design leads to a reduced computational complexity and improved data efficiency, which enables to efficiently capture all the large amount of upper channels, for example, the 131 brain anatomies in very detailed. Let's quickly look at the quantitative results of our model's performance compared to prior state-of-the-art and some baselines. And most of the methods have, you can see the infinite positive distance on the candy datasets, which we use as for evaluation. So this is because that some methods are failed to segment the entire like 131 anatomies. And we also have some baselines that are able to capture all the anatomies in human brain and present a fair performance. And we also can see the worm models, which is called Unity, achieves the leading performance compared to these baselines. Here's the box plot. We can show that significance of our model and the distributions of the testing data that compares to the prime models. And the star sign here indicates a statistical significance regarding the mean dice. Okay, so here's the visualization comparison across baseline methods and our approach, showing that our method has a better captures of boundaries and correctly segments of brain tissues. You can see that compared to the prior state-of-the-art extent, which in example like 27 3D units, and our method is a single network here can outperform that and achieve like a detailed segmentation of the interconnected boundaries of these human brain tissues. And we also have some like ablation experiments like that. We did some model scalability ablation studies on model parameters. So we have, you can see we have the small version of a model, which we called was the Unity S, and until we have a larger model, which is called Unity Large. The scale of the parameters of the models are different. You can see the details here on the table on the right bottom side, and we can see the performance on above, like figure A and figure B are two different evaluation data sets regarding the different size of a model of Unity. That you can see if we only use like 9 samples, like very limited, very low data region in the fine-tuning stage regarding the Colin and the candy data sets, you can see using a larger scale of the model like can perform better than the small models. So which is a consistent observation across the entire computer vision and the deep learning community, that the data the model scalability matters, and usually like the larger model, the better performance, but it also depends on how many data you're trained. For this scenario in our status, in our case, so we trained on almost 5,000 dataset and 5,000 samples, and fine-tuned on 50 manually traced cases. And our observation is that the larger models can achieve better, and the models are not underperform and can still converge into with a larger amount of parameters. And also on the bottom, you can see the visualization of how the larger and the smaller models performs compared to the ground truths. Also, we studied the pre-training like behaviors on how many pre-training data are useful to train a fair whole brain segmentation model. So in this talk, we are not using self-supervised learning strategies. In the contrary, we utilize in-domain supervised training. So we use some generated pseudo labels to train or to pre-train our model. The pseudo labels are generated by multi-atlas like registration methods. We manually selected like 15 atlas for the label fusion to obtain the pseudo training labels for collected multi-site data. We also we use these pseudo labels as a large-scale accelerate labels and employ for pre-training stage. And the same network fine-tuned on using 45 manual annotated labels on the OASIS dataset, and also evaluate on the Candy and Colin dataset with 5 samples. An interesting observation here is that you can see whether when we are using the supervised in-domain pre-training strategy instead of self-supervised learning, so we don't need that much data. See here, so we have, if we do not use any pre-training data here, 0 here means that we train from scratch. And we can see a very low performance, like around 69.5 on a DICE, on the evaluation cohort. And once we use some of the pre-training of the pseudo or the pre-training data here, like up to 125 here, which we achieve the best performance regarding the downstreaming task performance. Once the pre-training dates are more than 125, we don't see a significant improvement. So this scenario that we observe that increasing of number of pre-training data examples up to 125 results in the rapid improvement in the DICE score, and greater than 125 do not further advance the performance, and results fluctuate in a small range. Okay, yep. So let me quickly mention that as another part of this innovation of this work, we also have the radiologists annotated and curated hundreds of the kidney substructures data. So which is the first data set that we curated and collaborated with radiologists that can release the model for a kidney substructure segmentations, including the kidney cortex, medulla, and pelvis system, which is one of the part of this work. But today's talk is mainly focused on the whole brain part. Let's quickly see the rendering and how the kidney substructures looks, and we can go to a demo of my model integration. So this is the model comparison on the quality of the kidney data. And this is the iterator assessment and comparison with the developed UNST model and the menu. We can see the with our automated methods, the variance can be reduced. Okay, so let's have some closing thoughts today here, or a single model that called the UNST train that can outperform 27 ensemble models in the prior state-of-the-art methods. And we utilize a VIT-based hierarchical models, which achieves a promising performance on medical image segmentation, successfully modeling hundreds of tissues like in the human brain. And we also show good model scalability and data efficiency in low data region, and also the impact of the size of pre-training data compared to other methods. And we show that the UNST leads to the whole brain segmentation performance as a new state-of-the-art method, and it learns a general representation of vast number of tissues in human brain. And the pre-trained models can serve as a foundation model for other brain-related downstream tasks. Okay, so let me quickly show that how our models are integrated. So we have a Project Manai from Nvidia's development team that can deploy or the deep learning models within a project called Manai Label. So Manai Label can collaborate with multiple viewers, including like a 3D slicer. It serves as a platform solution for deploying the medical segmentation foundation models, which includes the integration of APIs and some samples, which also has a server and client design here. So this infrastructure for quickly deploying inclusive pathological radiology, which contains a Manai Label server and client. We also have some specific integrations and engineering designs for how to better visualizing the segmentations on 3D slicer. And let me quickly show a video here. So how the whole brain segmentation can obtain in the oops. Okay, it seems that the video cannot be shown here. Let me quick my be sure I can play this video here. Okay, so the video is broken. let me lively show the segmentation here. So here we have the 3D slicer setup, and we have the 3D slicer, and we have the MonaLabel plugin. And I have prepared a sample pre-processed with the MNI space data. We can see the MR data here. And once we click a button here using the MonaLabel plugin, we have loaded the model already with the UNST labels. You can see that we have the whole brain segmentation, including all the 131 anatomies showing up on the 3D slicer. And the entire integration is publicly available, so anyone can can download 3D slicer and download the model, pre-trained model checkpoints from the MONAI Model Zoo, and use or plug in the software integration to perform the whole brain segmentation. And also we can see that there's a segment editor in the plugin. So once you're interested in 1 or 2 anatomies, you can see that you could edit the segmentation in 3D slicer, and then you could submit the label and save your annotations here. So this is the engineering work for the integration of the UNST model. Okay, I think that's all of my talk. We're almost finishing in time. If you have any questions or you're interested in the model, please ask me or the team that how to get started with this open source. And we have the entire. Let me go back to my slides. Yep. We have our entire code and model are public, and we have our MONAI integration. And thanks to our collaborators and our prior PhD supervisor, Dr. Ben Lemon. Thank you. Any questions here?
Thank you, Yucheng. That's a very wonderful talk. We have a few questions from the Q&A box. A question from Syed Ahmed: is the registration to MNI 305 space rigid or affine?
Oh, it's both. It contains both. So we have the standard tools of registration, such as the ANTS. So we use ANTS, the tool from University of Pennsylvania, that can help us register the brain image into MNI space. But typically, from our experience, that both rigid and non-rigid steps are needed. Like in our experience, the pre-process step, we use both the registration steps to have a good registered reference image in the MNI space.
Thank you.
Yep.
Another question from Hao. Dr. Tang, thanks for your presentation. I have 2 questions. The first one, what are the dimensions of the input patch or the whole image? The second question is, what is the output of the model? A probability map of 132 channels. How do you handle that computation cost?
The image dimension is 96 by 96 by 96 as input. Yep. And the second question about the model complexity. We compared our studies on you can see the parameters here. So we have a very small model, which only contains like a 22.4 million parameters. But we can see that if we use all the training data here, we can achieve like around like 66 of die scores. If we scale a little bit up, like using a UNST base model, which contains like 87.3 million more parameters, we can achieve a very good performance, like around close to 0.69 dice of scores. So this is the model complexity. You can see that the larger model, which contains up to almost like 280 million parameters, but we don't observe very large improvement regarding the large model compared to the base model. So I would suggest that the base model, which contains a fair number of parameters at around like 87 millions of parameters, will be good enough to segment the whole brain anatomies like 131 tissues. Yep.
Thank you. Another question from Jingyi. Thanks for the presentation. Can the segmentation model work on brain images with tumors?
Yes. I think so. I think it works for most of the tissues. But we know that there are a very well-known public data that called BREADS, right, which has brain tumor images, which also contains the T1 weighted image. We can try that image for segmentation, but this model do not target on the tumor segmentation. So we do not include any tumor labels or ground truths in our training data. So I think that it can hardly segment the tumor, including the 3 types of the tumor labels. But I think this model can be used as a foundation model. Which can be used as a pre-trained model, and you can fine-tune on your tumor data set. Which I think it can turn out to be a very good performance regarding the breast data. Yeah.
Thank you. Another question. For the whole brain segmentation task, have you studied how the model performance varies across the 133 structures classes? Does it struggle more on smaller structures or structures that contain very fine or thin parts?
Yeah. We have evaluate everything. Let me quickly open a figure, which is a large figure, which I'm not included in my slides. If we go to the box plot here, so you can see every details of each class. We have the box plot created by our first author PhD candidate team, which you can see that even with the small anatomies like inside the human brains, we also have a very good performance. Like some tissues are very challenging. You can see that there are large variants. Like for example, this tissue. We can get a clear look at this table here. Some anatomies has large variants, but most of the tissues you can see have very stable performance, have like smaller variants here regarding the box plot. But yes, we do see some very challenging tissues that even with the larger models, which up to like 280 millions of parameters, is still challenging to segment because it's too small. Like in MNS space, in the brain image, like some anatomies only contains several pixels, so it's very challenging to segment these very small tissues. And also tracing these small tissues are also very challenging for the doctors, the radiologists. We don't think that the ground truth labels are perfectly aligned, but that's what human can do. Yes.
Yeah, thank you. Following up Jenny's question, you mentioned that your model is not targeted on brain tumor, but did you test your model on labeling normal brain areas in the presence of large tumors like on breasts?
We do see some. We do try this, but we don't evaluate it yet. Yeah, we have some brain images loaded up into the 3D slicer, and it works on the segmentation on the human brain on a tumor that the brain data contains tumor from breast data, which is the T1 weighted images. But we don't evaluate the whole brain segmentation on the tumor data set. We don't have the numbers and the quantitative performance. But we do see it works like qualitatively. Yeah, if you load it up in the 3D slicer and you apply this model for segmentation, you can see the segmentations can show up on the brain image with the tumor. Yeah.
Thank you. Another question from Matthew. I have seen 3D unit segmentation results where sometimes the regions are disconnected. For example, thalamus could be split into 2 disconnected regions. This is not very well captured by DICE. Have you checked to ensure that segmented regions are properly connected?
Yeah. Let me share again the 3D slicer. let me scroll a little bit down to across the brain, so you can see that how well the model predicted labels are regarding the interconnected tissues, like for example the corticals and the white matters and the tissues and structures. I think our model, we don't say it's perfectly differentiate the boundaries of the interconnected structures, but it can well captures the boundaries and the interconnected details. So I think that's one of our advantage of our model compared to the other or the prior models. And you can see the rendering that there's very good details. It can tell different tissues and sub areas in the brain. Yep.
Yeah, thank you. Thank you so much for thanks so much, Yucheng, and thanks so much for all the 3 speakers, and thank you for all the audience for attending this event. For the recording of this event, after we get the permission from the speakers, we will publish on our YouTube channel. If you go back to the advertisement email from MICCAI community, you can find that link to that YouTube channel at the end of the email for this MICCAI industrial talk event. Thank you so much for to all the speakers and to all the audience. Have a nice day. Thank you.
Thank you, Sam, for hosting.